Hi, Alex here again. Now, the further example 7. So we look into further example 7. The question says, now, a shaft made of mild steel is required to transmit 100 kilowatt power at 300 revolutions per minute. Now, the supported length of the shaft is 3 meters. Now, it carries two pulleys, each weighing of 1,500 Newton, supported at a distance of 1 meter from the ends respectively. Now, assuming the safe value of shear stress to be 60 megapascal, and find the diameter of the shaft. So here's the diagram. So you can see there's a shaft. Okay, I have noted it as A, B, C, and D. And then total length of the shaft is to be 3 meter. And then we have pulleys with 1,500 Newton each, supported at a distance of 1 meter apart. And then the pulleys are placed, okay, at 1 meter from each end. So it's 1 meter from each end, so you have 1,500 Newton. So to find both this reaction here on the supports, you have this shaft here actually is supported symmetrically. So you have symmetrical loading. So what you can do is take 1,500 plus 1,500 Newton here. So you have altogether 3,000 Newton of force acting vertically downwards. And this total vertical downward force, which is 3,000 Newton, will be equally divided between the two supports. So therefore you get 1,500 and 1,500 Newton. So you can use this way in finding out the reactions if the shaft or the beam they are symmetrical. Otherwise, you have to use a condition of taking moment about a point, a reference point, where the resultant bending moment is equals to 0 to find out one of the reaction. And then the second condition is to consider the total vertical forces equals to 0 in order to find out the next reaction on the support. Now, if that is not symmetrically loaded, so you have to follow both the condition, summation of moment, total moment is equals to 0, and the summation of vertical forces equals to 0 in order to find out any reactions on the supports. So now, first, again, the same thing, power is given, the speed is given in revolutions per minute. So we can use this formula in order to determine or find the torque that is required. So 100 times 10 to the power of 3 based on 100 kilowatt and 300 revolutions per minute based on what is given in the question. So you will be able to find out the torque of 3183 Newton meter. So then after that, what we need to do is we need to calculate the bending moment from point to point. That means if we are moving from left hand end, so we must consider from point A, then move to B, move to C, and move to D. So if we, let's say, consider from left hand end, from the left hand end towards the right hand end, so we have to move from A, B, C to D. And we only can consider anything that is before the point that we consider. If let's say I put a point A, so anything that is on the left hand side should be considered, not on the right hand side. Okay, so if let's say I consider point B, I only can consider the things or the stuff that is at the left hand side of the force or of point B, and then see anything on the left hand side of point C, not on the right hand end. Okay, if you were to move from left to right, then when you consider point D, then you have the whole beam that is on the left hand side of point D. So you move from point to point. So at point A, the bending moment is 0. Why? Because if let's say, for example, we consider the reference is at point A, so the distance between the force 1,500 Newton to point A is actually 0 distance. So if you have a force of 1,500 Newton multiplied by a distance of 0, you will get a bending moment of 0 Newton meter. So then when you move to point B, the same as for the 1,005 multiplied by the distance 0, So if you, let's say, for example, consider now the reference is at point B, and of course the distance from the reference at point B to the location of the force 1500 Newton here would be 0. But anything on the left you should consider, that is 1500 times 1 meter, and which will cause the shaft to bend upwards. So when the shaft bend upwards, you consider that as a positive bending moment. So you got positive 1500 Newton meter. And then when you consider point C, the same thing also. Point C, the moment at point C for this 1500 will be 0, but you have 1500 times 2 meter positive, and then you have 1500 Newton multiplied by 1 meter negative, because this force multiplied by this length here from B to C will give you a bending moment causing the shaft to bend downwards, whereas this times this length here, the force here times this length would give you a bending upwards. So you have positive 1500, okay, multiplied by 2, then minus or negative 1500 times 1. So the resultant bending moment at point C would be 1005. Then at point D, the same thing, 1500 times 3 positive, then minus 1005 times 2 minus negative, and then 1500 times 1. Okay, so the resultant should be 0 here. Okay, that is because earlier we have considered that the shaft is in an equilibrium state. So the resultant bending moment, as when we consider the entire shaft, the resultant should be 0 for any simply supported beam or shaft. Okay, so once you have got the bending moment from each point, so now you can actually draw a bending moment diagram based on the space diagram given below, above. This is called the space diagram. This is the bending moment diagram. So 0 at point A, so this is your point A, so starting from 0 here, then goes up to 1500, so you draw a line connecting point O to point B here, A to B. So it's 1005, and then between point B and point C, the bending moment is constant, and then from point C to D, you can see it is going down to 0 at the end of the point, at the end of the shaft, the entire shaft at point D. Okay, so now that is, from here we have to select which is the maximum bending moment. So, and of course when you see the 1500 is the maximum bending moment. So now once you have got the moment and the torque, now of course you can find out the equivalent twisting moment. So by putting in 1005 square, by putting in 3183 square here, square root, you will be able to find out the TE, which is 3519 Newton meter. And also based on TE, you can also say that it is equals to pi over 16 times d cubed times tau max. The tau max given here is 60. Remember, once shear stress is given, the best is to consider TE, not the ME, not the equivalent bending moment. So you have to consider the equivalent twisting moment, so that we have found. So from here we can find out the shaft diameter if we substitute the 60 megapascal here. So the diameter of the shaft will be 66.8 millimeter, or you can take it as 70 millimeter. And that's all for example 7. Thank you very much for watching the podcast. Any comments or questions, please put on my comment section in my YouTube channel, okay, under the section of shaft design. Thank you very much, and see you again. Have a nice day.